In this problem, we're given an unknown acid, and we're asked to determine the Ka of the acid. So this is going to be another equilibrium type problem. Before we set up our ice table, we do a couple preliminaries. First off, we're given the moles of the acid and its final volume, but whenever we're doing equilibrium problems, we want to work in concentrations. So let's convert these into molarity. So remember that molarity is equal to the moles of solute, in this case the acid, divided by the total volume of the solution. So I have 0.250 moles. I need the volume in liters, so 655 milliliters divided by 1,000 gives me 0.655 liters. And so my initial concentration of acid is 0.382 molar. Now, we're also going to need the hydronium ion concentration, so let's go ahead and convert the pH into a hydronium ion concentration. So H3O plus is 10 to the minus 3.44, or 3.63 times 10 to the minus 4 molar. Now we're ready to go ahead and set up our ice table. Alright, so our initial concentration of the acid is 0.382. Of course, I don't worry about the water because it's a liquid. I don't have any hydronium ion or conjugate base before the reaction starts. The change in HA will be minus X. The change in H3O plus and A minus will both be plus X. Now, if we look at the equilibrium row of the table, we can already know what some of these values are. And specifically, because we're given the final pH of the solution, we know what the equilibrium concentration of H3O plus is. And so that means we also know what X is. So X is 3.63 times 10 to the minus 4. And because the equilibrium concentration of H3O plus and A minus are both going to be X, we also know that A minus is 3.63 times 10 to the minus 4. And we know that the equilibrium concentration of HA is going to be 0.382 minus X. And so to three significant figures, that concentration is actually unchanged. So this is a good example of when X is small. This is why we can ignore it in some of the other types of problems that we do. So, now that I know the equilibrium concentrations of HA, the hydronium ion, and the conjugate base, I can just plug these into the equilibrium constant expression, and that will give me the value of Ka. And so we'll do that on the next slide. So I've just retyped our ice table a little bit more neatly, and we can go ahead and calculate the equilibrium constant, or acid dissociation constant in this case. So I have 3.63 times 10 to the minus 4 for the H3O plus, and because the A minus is the same concentration, I can just go ahead and square that, divide that by the concentration of the reactants, and so when I plug that into my calculator, I get that my equilibrium constant is 0.382. And this is what the problem was asking for.